So maybe the right place to begin is just kind of chatting about what I view as some of the like big picture themes that are going to come up again and again throughout everything else I'm saying. So I think probably the biggest thing I've changed my mind about over time is when I got into the field, I was very excited about this vision of ambitious reverse engineering. This idea that we could take these weird interpretable neural networks and reverse engineer them to something human understandable. I now basically think that the strong versions of this dream seem pretty doomed, but that we have made way more useful partial progress than I expected. And I think that there's just like a bunch of stuff we've learned how to do that is just already useful, even though it doesn't really come close to this initial dream of fully understanding things. And I'm now a lot more excited about work that is just leaning into the pragmatic vision of how do we achieve goals that we care about using the kinds of tools that trying to understand these systems has given us. How far can we push this understanding while accepting that I'm pretty pessimistic on getting all the way to fully understanding things. I don't really think this works for reasons I'll get into. And I think maybe another kind of crucial theme is this idea of where does your information, like, how do you tell if what you're doing is bullshit or not? I think that a pretty critical question that every interpretability researcher should regularly ask themselves is like, how do I know that what I'm doing is not bullshit? How do I know that what I'm doing is actually telling me something interesting about real world phenomena? And kind of what empirical observations would be different if I was right or wrong? And maybe a final big picture theme is the idea of the linear representation hypothesis, where, in my opinion, a consistent theme behind most interpretability findings has been stuff is just really linear. This did not have to be true, but it seems pretty true. This could have broken in many ways, and largely does not seem to have broken. And I think that just kind of observing a bunch of the evidence that has accumulated over time that most things are linear can be instructive. All right. Any questions on these three big picture themes? I think if you don't feel clear on exactly what I mean by each of these three, now is the time to ask. All right.
What was it? So what do you mean by sources of truth and downstream tasks?
Like
as distinguished from pragmatic understanding?
By sources of truth, I mean, how do you ground your research? How do you tell the difference between a true hypothesis and a false hypothesis? I didn't actually explain downstream tasks. What I mean by downstream tasks is the idea that you can form, maybe I should make this into a subpoint. There are two key ways historically people have tried to argue that their interpretability research worked. The first way was what I think of as like how accurate is your interpretable approximation? Kind of you try to reconstruct part of the model in an interpretable way, like reconstructing it with a sparse autoencoder, or you try to like make predictions about the model's behavior using the algorithm you think is happening, and you're like, is this legit? What's my error? Downstream tasks is a conceptually different way of grounding your work, where you say, what are the things I can do with this interpretability technique that I could not previously do? one of my favorite examples of this is the auditing games paper from Anthropic and Sam Marks, where they gave a model a hidden goal by training it on fake documents and doing a bunch of other really galaxy brain stuff. And then they had researchers compete to see if they could figure out that hidden goal. And the researchers were blinded. They didn't know what they were looking for. And this is a completely different way of figuring out if SAEs are interesting. This is saying, can people find things with SAEs better than they can find them without SAEs? And this is a very different thing from the idea of applied interpretability. Yeah, it probably deserves to be another. So another question/theme is how much what you're trying to do is just pursuing understanding for understanding's sake, as kind of as far as you can go, versus trying to just do a useful task. And if interpretability is the right way to do that task, great. If interpretability is not the right way to do that task, that's also fine, but you're going to do something else, which I think of as applied interpretability. And kind of the middle ground, which I think of as using interpretability to understand the broad strokes and qualitative properties of a model, which you could either be doing because you are pursuing this for understanding's sake, basic science, or because you think this is useful, but you're not trying to like go super deep into the model. And yeah, I'd probably just make this a separate axis. Reverse engineering versus like trying to figure out the like high level properties and the broad strokes without stressing about have you gotten every single last detail. And a confusing point that I think is important is that there is a big difference between I want to look at a real world task in order to figure out if my interpretability technique is doing something real or not, but I don't actually give a fuck about this task. And I'm doing a project about solving this task, and I'll only do interpretability if it is the best way to solve this task. The first one, downstream tasks as a source of truth and grounding, is just a way you can do an interpretability project. And the second one is more like applied interpretability, or possibly even just machine learning, where interpretability is one of many tools you're considering using. And I think that it is extremely compatible to do basic science with downstream tasks. How much sense am I making to people? Great. Arya?
My question was about the linear representation hypothesis. So it's not super clear to me why this is surprising, in the sense that, like, if it wasn't linear, what would that look like? Like, if we're trying to steer things, it kind of wouldn't steer very clearly. Like, what would that other world look like?
I mean, why does steering work? This is not a priori obvious. Like, it was, well, I mean, I wasn't massively surprised when I saw the first steering results because I already had linear representation shaped intuitions. They're just like, I think something that's like probably harder to appreciate is just like how much we used to not know about what happened inside these models. Like back like 5-10 years ago, not 5 years ago, back like 10 years ago, I think we had some like super preliminary results. I think people had looked at things like linear probing and like maybe had some results that maybe worked. But the prevailing wisdom, as I understand it, was, man, people spent decades trying to understand this shit, and that led to the first and possibly second AI winter. This is dumb. Just YOLO. Make a benchmark, hill climb it. You're never going to understand it. This is fine. I'm sure this is a faithful description that would definitely pass people's ideological Turing tests. And I think I think that it is it would have been extremely not obvious to someone of that worldview, to think that we can just take the difference between activations on some prompts and then add it and it will just work. Like, what? Why? This is such a specific way for the inscrutable pile of matrices to work. I struggle to conceive of interesting ways things could work and be interpretable in a way that isn't linear. You could imagine, say, linear probes don't work, but non-linear probes do work. And we'd never find a way for linear probes to work, but it does seem like there's some real information inside these systems. That would be perfectly plausible a priori to me. And like various other things roughly within that vein, but we could just have no fucking clue what's happening. I don't know how satisfying an answer that is. But I think it should not be taken for granted that neural networks are weirdly understandable and weirdly nice. And this was not obvious to me before I got into the field that any of this would work. All right. Any other questions? Great. So I guess I've kind of already been talking a bit about let's call them the dark days. Where, to be clear, I think that there were interesting hints of what was happening that would not have remotely called themselves Mech Interp. People discovered things let's see. There was people discovered things called Gabor filters that were early layers in convolutional neural networks. Let me just switch window. So people observed, I can't even remember when, that if you look at early layers of a convolutional neural network, they often seem fairly interpretable. And they're not aware, some of the earliest kinds of real deep learning people got excited about with some image classification networks like DANnet and AlexNet that were convolutional neural networks. The way convolutional neural networks work is you have a really simple linear map that's 3 by 3 or 5 by 5 matrix, and you apply it to each 3 by 3 grid in the image, and you could see things that were identifying edges or corners, where you'd have +1 on the top and -1 on the bottom, and this is a reasonable way of detecting an edge. But beyond this, it was kind of less clear and somewhat messier. I think that I'm not super familiar with the exact details of early interpretability work, but there was this pretty famous paper, note the 25,000 citations, on visualizing, understanding convolutional neural networks, that has some pretty pictures in it somewhere. I think this might have been one of the first papers that talks about saliency maps. I honestly don't remember the exact technique used in this paper, but I think they did things like look at maximum activating dataset examples for neurons and were like, this seems pretty legit. Look, these cells, they have patterns, they are not random, and they did something to create visualizations. And yeah, so maybe skipping ahead a bit, I think there were like some hints things were going on, but many people in machine learning thought that interpretability was a bullshit dead-end pseudoscience. In fairness, much of the interpretability research was, in fact, a bullshit dead-end pseudoscience. So reasonable. But they were also somewhat pessimistic on just the idea that you could do any of it. And in my opinion, Chris Olah did a lot to kind of push forwards this idea of we can just like dig deep and understand these things, and the neurons seem understandable, the weights seem understandable. Again, at the time, people were like very into image networks and convolutional neural networks. And so there was this famous paper from 2017, feature visualization. The key idea was take a neuron in this network. I think they were studying Inception V1, this like 2014 image classification model from Google that Chris's team spent several years going extremely deep on, and basically optimize it using gradient descent to optimize images to make the neuron light up a bunch, doing a bunch of like tricks to make it not look like a bullshit mess, and saying, look, this seems coherent. And this is, in fact, the thing that neurons seem to be trying to look for. You can get these weird psychedelic things that seem like dog noses, maybe. And I think they also lit up on pictures of dog noses. Or this, which I assume is some kind of texture or some kind of clothing. Fun fact about ImageNet, the data set that many of these early models trained on, it has a ridiculous number of breeds of dog in it. So these models are really good at figuring out breed of dog and have a lot of dog-related features. And apparently Chris' team learned a great deal of things about how to subtle details of dogs that help you identify what breed they are. And I think that this was one of the first papers which was introducing a tool that you could use to try to understand what a neuron meant. They also have observed some signs of polysemanticity, or is in this paper? I think there was something in this paper about polysemanticity. The enemy of, no, not this one. All right. There was some paper around this time that observed polysemanticity for the first time. I am not going to claim any confidence in which paper that was. But kind of starting to make a big deal out of sometimes neurons seem great. Sometimes neurons seem like a mess. We're not really sure why. In later layers of this model, more of them seem like a mess. And yeah, I think to me, a lot of what is exciting about this paper and the kind of line of research it represents, highlighted here, is I think that there's started to feel like evidence that you could break these models down, that not only were there meaningful directions, but that these directions were just literally the neurons, the standard basis of the model. And a priori, it is not obvious. Even if you think there's something linearly represented, it's not obvious. It should be aligned with the standard basis. I think people kind of noticed arguments like, well, activation functions are aligned with the standard basis, which means that it's more reasonable for things to be it's like more reasonable for neurons to be meaningful in arbitrary directions. Like maybe this isn't super surprising. Part of, and I think part of why this matters is, well, first off, it makes your life dramatically easier because you can just iterate over the neurons in a for loop and do feature visualization rather than trying to figure out the directions. But also, if you already have a prior that the neuron means something, and then you look at the dataset examples and they have like a coherent pattern, then having the feature visualization also aligns with that pattern, then you're like, well, I'm pretty sure that explanation and these things align with that explanation seem good, I guess. While if what you're doing is more like, I want to, here's a random direction. Does this thing mean anything? You should put a much lower probability it means something, and thus the bar for evidence required should be. Though I think it took a while before people could reasonably claim that there was enough evidence to have a prior that neurons would often mean things. All right. That was rambly. Hopefully I gained like some vibes. I'm going to stop here for questions. L?
Yeah, I guess this like seems like a big difference between like these models where the neurons mean something, and at least how I'm understanding like the sparse autoencoder work where it's the neurons don't mean things, but there is. Okay.
Great question. That comes later in the saga. Anyone else? Cool. All right. So, for context, this is a website called Distill, which is like an online journal set up by Chris Oler and some other people who wanted academia to have better standards and also not use fucking PDFs and actually let you embed interactive things. It was a beautiful and noble effort, and it didn't really work, and they got really burnt out, and it got shut down. It was very sad. But there is still a bunch of great papers, including a lot of the early Mech stuff. One fun paper is the building blocks of interpretability, which kind of is arguing the case that there's like a bunch of things you could try doing to interpret these models. Here are like various tools and things you could use, and also it's really important to have good interfaces and tooling. And remember, this was in the days before vibe coding when making interfaces was hard. And I think that an interesting accident of history is like a bunch of the researchers involved at the time were like pretty good at web development and liked making a bunch of interfaces. Let's see, is this the one about placementicity? Oh, they have a hyphen, and they mention it once, but they do mention it. Though it's a sufficiently obvious observation that probably mentioned in other papers. And another fun one is the activation atlas paper. This really goes all in on the interactive interfaces are important. This is some kind of weird visualization of all of the neurons in this image classifying model in different layers, or I don't remember exactly what this is visualizing. I think it's neurons. And or maybe just taking different points in activation space after some dimensionality reduction, and looking at what the model classifies them as and doing a feature visualization on them and being like, look, you've got like acorn groups, acorny things over here, that kind of transition to things that look more like plastic bag-like or fabric-like, or well, this is turning into what looks like an arm or maybe a leg. Anyway, very fun. You might enjoy clicking around with it. But one thing I want to highlight here is this particularly fun result where they made an interpretable adversarial example where they had a picture of a gray whale and they stuck a baseball on it, and now the model thinks it's a great white shark. And anyone want to guess how they made this? Feel free to just call out and give a guess. Or like how they thought of this, making it easy. Or like why it works.
Is there a neuron that perhaps like corresponds to both baseballs and great white shark?
Kind of. Warm, but not quite. Anyone else?
Guess I'm wondering, like, that's the color of the baseball, and so like it's a great white shark, and they put a white object in there, so maybe this is pushing it in that direction.
Cool.
Yeah, something similar. I guess shark is plus white is put in the direction of great white shark.
Cool. So I believe that what happened is they were doing something like looking at how the model. I can't remember what the exact story was. It was something like they were looking at things that helped the model, that made the model think something was more great white sharky or like very whaley. And they observed this kind of teeth-like thing that also seems to look pretty baseball-like coming out of feature visualizations. And I think that there's basically some neuron that seems to both detect the stitching on a baseball, red stuff, and a great white shark's teeth, which, kind of also like red zigzags on white. I don't know what sent me to. And so they are like, well, what's a great white shark? It seems like it's like a kind of whale-like thing plus teeth. That's basically a baseball. What if we glue them together? And in addition to just being hilarious, I'm highlighting this because I think it was one of the like great early examples of grounding with downstream tasks. The downstream task here is make an adversarial example that is clearly not a great white shark, that the model thinks is a great white shark. And is this an interesting task? But I think it is like not trivial. And the fact that they were able to like make this kind of prediction and construct the image and it worked was like pretty good validation that that tooling was telling them something. And historical detail. So the next any questions on that? Great. All right. So the next interesting cluster of things is going beyond studying neurons and activations to studying weights and circuits and algorithms with this. And again, the kind of public knowledge, the public results up to this time, as I interpret them, were kind of like, yeah, it seems like there's like some understandable stuff in the model's activation. This like neurons often kind of have this interpretable meaning. It's not necessarily like perfectly rigorous or perfectly clear, but it sure seems like something's happening here. And so what Chris's team did is they basically just have this string of like tiny blog posts exploring different parts of this hypothesis that the model's weights just represent interpretable algorithms. And if you understand what all the neurons mean, you can just read off how each set of neurons goes to the next one. And I don't know, they had this like position PC post making a bunch of claims like features of the fundamental units. They seem pretty linear, probably. What's the yes. They even talk about the idea that maybe it's a direction, rather look like combination of neurons rather than a specific neuron. This idea of like features are connected by weights and that we can understand them, and which is kind of want to highlight here because I think it was like the interesting one. And then this claim of universality, which was like nice, but in my opinion, somewhat less central. And like, it's all would be an extremely big deal to me if every neural network was interpretable, but you had to do a bunch of extra work for each one. And I think the most interesting examples of work here, one is high-low frequency detectors. These are a type of neuron they found that basically detect kind of sharp bits next to blurry bits in images, which you might expect from like, there's like a figure in the foreground and a kind of blurry background that wasn't in focus or something. And I believe some neuroscientists since found evidence of these in the brain, which is kind of funky. And circuits wise, I think that the curved circuits work was excellent and still a good contender for one of the most rigorous circuit analyses in a real model that I know of, where they basically identified a family of neurons early in the model and said, these sure seem to be representing curves, and the curves seem to be getting more complicated. Like, we start with like lines of different angles, and they seem to get combined into more lines, and then maybe they're curving a little bit, and now they're just curves. And convolutional networks kind of draw information from the local area into a neuron. So this kind of slowly becoming more and more abstract checks out. And they had like a bunch of evidence that they had in fact understood the algorithm. The one that I found most persuasive was one of them just wrote a Python program to regenerate the weights based on their human understanding without without referencing the weights, and then just substituted that in as an artificial neural network, and found that it seemed to recover in about half the performance that was lost when you deleted the curve detecting neurons. And to me, the interesting historical context here is, I think that this was one of the like best examples that maybe we could just look at the model's weights and understand it. And there were just loads of structure here. This would be a pain, and there were like some things that need to figure out, like polyspecificity, but like the dream of ambitiously reverse engineering the thing felt pretty alive to me at the time. All right. Any questions on this? Also, can I get people to put in the chat? Would you like me to go faster, slower, or about the same speed? Since I have no idea how much of this was just obvious review to people or incomprehensible gibberish. Cool. All right. No questions? Great. All right. So now, this came out in like 2020. At this point, I think it was pretty obvious that like language models were the shit, and also that, I know GPT-3 came out that year, and it started to seem much more real that we could, the path to AGI would just in fact be stack lots of data and lots of computing power and hope for the best. And so people became way more into language models. And Anthropic got founded at the time, and Chris Olah, who'd been like leading much of this research, co-founded that and started a tech team there, and also hired me, which was very nice of him. And I think at the time, I remember being like, and kind of initially had just been very skeptical of the entire institution of interpretability, and had thought that like, it seems like isn't the prevailing wisdom that we can't understand these things and it's all a mess. And I think that I then saw the image circuits work, and I was like, oh, this seems pretty cool. But I don't know, it seems like images are really nice. It's continuous. You can do things like feature visualization, and it seems like there's maybe less stuff than language. So my intuition was, I don't know, it's like pretty not obvious to me that we can extend this to language models. But also it sounded like a cool vision and really interesting to try to help with. And I joined after most of the work on a mathematical framework had been done. But I view this as one of the first papers trying to like really explore what it might look like to reverse engineer a transformer, and a bunch of fundamental ideas like the residual stream is the central object of the model, not just like a weird thing. I don't know. People used to draw neural networks where they'd like draw each layer as a box, and the residual stream is like kind of arc round. And this paper was the first place, at least I saw, people writing the residual stream as the central thing, and like layers as like cute things you add on that are incremental updates. And a bunch of ideas around like how you can think about attention heads, which were the seemingly weird, annoying new thing about transformers, and in hindsight, actually way nicer than MLPs in a bunch of ways. And I think that, I kind of went in being like, if this is really going to work on language models, and then things just seemed really nice. We found induction heads. Induction heads turned out to be like such a big deal. They caused a bump in the loss curve, and this was very exciting. But we were kind of working with these tiny models, and when people had, when we tried to look at, when we tried to look at MLP layers, occasionally the neurons were interpretable, but Chris's vibe seems to be, this seems like a fair bit less interpretable than image models were. This is kind of weird. Not really sure what we need to do here. This seems like a big problem, but I'm like, the thing to figure out post attention. Then so a few months after this, I left Anthropic and worked on Grokking. And I'm assuming many of you are like kind of familiar with the vibe of the paper, and not going to go into too much detail, but stop me if not. But Grokking was this like big mystery. It was super fashionable to work on at the time. It involved a 2-layer algorithmic model, and I was like, this is a pathetic model. This is tiny. Surely Mechanistic. If Mechanistic can do anything, it can figure out what the hell's going on here. And I was right. Found this really pretty modular addition algorithm, and went in not really expecting to see this, though I did discover after the fact that some parallel researchers had kind of come up with this algorithm a priori, but not written it up yet. So it wasn't exactly deeply unexpected, but it's kind of weird. I didn't expect it to be using a trick like this. And this kind of was a thing we could look at during training, because we now had these like nice metrics, and this gave us a bunch of insights, and this all just seemed very exciting to me. And it seemed like, man, we kept having opportunities for ambitious reverse engineering to fail, and it's just been going pretty well. I think there were like some warning signs accumulating, like polyplanticity was a big one. I think another big one was we definitely had not completely reverse engineered any of these models. I think this was like the closest, but there was still some weird unexplained mysteries. For example, the way it worked is it was doing Schrödinger entities in some frequency, and it didn't really matter what frequency it picked. It seems to be using 5, but for some reason it was also using frequency like 30 on the inputs, but it didn't appear on the outputs. Why? Who the fuck knows? Never figured that one out. Maybe this was a random vestigial thing. Sometimes during training, it would like start using some frequencies and then switch to others. And I feel like I understood enough of it to be able to say some pretty interesting things, and that kind of seemed like the important thing at the time. But in hindsight, this seems like, even at the time, it was like, yeah, I'm like completely understood that. Maybe I could if I tried harder, maybe not. Unclear. And I think with a mathematical framework, there were like various heads we didn't understand, and the things we were doing just really wouldn't scale. Like we were doing things like saying, well, each attention head is kind of like a linear transformation you're applying to the model. We're applying like one per head, and we're also doing the identity from the residual stream. But now if you apply the second layer, now you have every pair of heads. So you've gone from like 8 to 64, and if you do 3 layers, now you get to 512. And if you look at a real model, which even at the time were like massive, or at least people liked working with massive models, that'd be a separate weird thing where model sizes have not got that much bigger since GPT-3. They're just trained on way more data. And this does kind of confuse me, but separate questions. At the time, we were like, GPT-3 was about 180 billion parameters, and it was dense because obviously all interesting models are dense. And yeah, surely it's going to just, keep getting bigger. That seems reasonable. We can extrapolate out, like, it'd be like a trillion in like a year, and then even worse beyond this. And then, maybe GPT 4.5 was that kind of scale. We don't really know. But also, definitely, I didn't really want to monetize GPT 4.5. So, that was another anomaly. But I view ambitious reverse engineering as looking like reasonably good at this point. Like, any questions on this before I go on? And in my opinion, ambitious reverse engineering has just gone extremely badly since. And we have made, in my opinion, very little progress. On specifically the goal of pursue an agenda that I think can realistically understand everything important about a model and give us a fair amount of confidence that we're missing nothing. And so, maybe walking through what happened next, I think there were maybe 3-ish. So call that the light days, and then emerging strands of research where I maybe say that between a mathematical circuit, mathematical framework, and now there were maybe like 2 big popular waves of research. Causal intervention based circuit finding and dictionary learning, and superposition. I'll maybe just analyze these separately so that you can kind of think of them as parallel things. So the thing that first got me excited about causal intervention-based circuit finding was the Rome paper from like David Bao and Kevin Meng, where they basically took activation patching, which had kind of already been studied a bit in like a prior paper David Bao was involved with, but I basically haven't really seen elsewhere. and showed that you could use it on either a pair of prompts or like a prompt and a prompt plus Gaussian noise to try to figure out which chunks of the model were important for some tasks. And they got this pretty exciting and fairly refined vision of like, well, you take a prompt like Shaquille O'Neal with a Neal ending here, or Megan Rapinoe ending here, plays the sport of what do we patch to make it say the sport that is true for one of them. And oh, look, it seems to live on the final token of the subject. And then it kind of like fades off with like some sharpness, and then moves to the end. And I think that this was pretty cool. I think this was like some of the first work I saw that felt like it was helping understand factual recall. It was kind of like token specific, and it sounded like you could read quite a lot of information from this. They also did some like layer specific stuff. It's probably in the paper, but they got things like, MLPs here seem important, and then attention layers here seem important. And in my opinion, this is the interesting half of the paper. There was also another bit that was about fact editing that was the thing they framed as like the main contribution, but I think was like less exciting and largely just a form of specialized fine tuning to kind of insert a fact into the model. Al?
Oh, yeah, I was just going to ask, I don't think I understand this plot or what exactly this paper is doing. So it'd be great if you could add a little more detail.
Sure. Do you understand what activation patching is?
I don't think so.
Right. All right. So activation patching. The people may have seen it under the myriad other names it has in literature, like causal mediation analysis, causal tracing, interchange interventions, resampling, ablation, random shit. All right. So the idea is basically we think that a sparse set of model components are important for some task. Here the task is answering like Megan Rapinoe plays the sport of with soccer. And so we want to do equivalent, we kind of want to do a for where we pick a component or set of components, we somehow change it, and then we observe the effect on the output. And the reasoning goes, if you affect many things, then you, like, yeah, if it has a big effect, then it was important, otherwise it was not important. The naive version of this you might do is just replacing the model activation with zeros. Can anyone see what goes wrong if you do this? If you're confident you know the answer, leave it.
What was the question again? Sorry.
What goes wrong if you try to understand, say, which MLP layer matters for this task by, like, say, maybe let's be more specific. You want to understand the MLP layer that contains the fact that Megan Rapinoe plays soccer. And you want to do this, and a candidate method is that you just replace the output of a certain MLP layer on a certain token with zeros, and you look at how much that changes the final answer. Does that make sense? Great. What could go wrong? Crazy guesses encouraged. All right, so we have in the chat OOD activation patterns. But like, that's not really an explanation. It's a factor that could lead to something, but like, why would being out of distribution change the model's output if it wasn't important for the task? Like, if an MLP layer doesn't contain the facts, why does throwing it off distribution matter? All right, other guesses in the chat. Redundancy is a valid answer, but not the kind of key factor I'm highlighting here. layer norm is a fucking pain, but you can kind of ignore it most of the time, including here. And so, just to clarify, I'm not saying zero out a specific neuron. I'm saying zero out all of the neurons in one, or like zero out the output of a layer. All right, here are some things that could go wrong. Great. All right, Alex, you got one. Removing other concepts that might matter. For example, if you remove the model's ability to speak English, you're going to have a bad time. And if all you're observing is the probability of soccer, you might see that go down a bunch because the model has no idea what's going on. And this does not mean that you have found the fact. Another thing that can go wrong is that the model was relying on this. The model was kind of relying on the activations having a certain mean or a certain norm or something. And by making the layers zeros, you've shifted this in a way that like breaks assumptions that later layers were depending on. This kind of effect is why if you steer with too large a coefficients, everything goes wrong. And I think that, let's see, I don't want to I think that, another factor is you could have just found something that is like important for the task for reasonable reasons, but is not where the factors store. Like maybe you found the thing that's about figuring out that you should say soccer rather than football in this context or something like that. Actually, in this context, it probably just says both about 50-50, but maybe more soccer because the internet is American. But so the partial solution to this is called activation patching. The key idea is to set up a pair of prompts that are like as close together as possible, but differ in some key detail. This is also known as a contrast pair. And I think they are like one of the most important insights in interpretability, that you can do this and it's often really helpful because most things will be similar and controlled between the two, but not everything. And in particular, if you take the like Shaquille O'Neal or the Mech and Rapinoe one, then you would hope that, it's got to speak English in both, and it's got to know that it's doing factual recall, it's got to know what a sport is, but it will get a different sport. And this doesn't rule out things that maybe it's the soccer football thing, but what happened was, it looks like NLPs here are very important. This graph is not about NLPs, so maybe I'll just go to the paper, since that's probably making things even more confusing than needed. So the middle green graph is like you do a replacement. Here they're doing like an interval of 10 layers at once. So like this actually means layer 10 to 20. But that's not a super important detail. It just makes the graphs look prettier and is a bit less precise. Also, meta note, every time you see graphs like this in a paper, you should assume they have cherry-picked this to look good, and a randomly chosen example does not look as good unless they explicitly say otherwise. Or they average across a bunch of inputs or give error causal. But, anytime you see a figure go viral on Twitter, assume it is not representative and cherry-picked. Otherwise, you will have incorrect beliefs. And so to me, the exciting thing about this is you can kind of start to piece together some notion of what's going on here, where like we can kind of see here that MLPs seem important. Can anyone tell me why it's interesting that MLPs light up on the last token of the subject rather than, say, the final token?
So maybe
No, go ahead. Rash.
so maybe the attention transfers the information to the last subject token, and the MLPs do the job of collecting information about the subject.
But like, how does it know that we want a sport, a location? Like, it doesn't say is in downtown. This is really important information for answering the question. What's going on?
I'm not sure now.
Simon?
So maybe the MLP is kind of a key value, and then it's kind of a key for a lot of things which is associated with the Space Needle. And one of them could be Seattle, but it could be also any other thing. And then later on, the attention picks the one which it's the later part.
Yep, pretty much. So what it turns out is happening here is we can, what kind of seems to roughly be happening is it just looks up everything it knows about an entity on the final token of the entity, or a token near the end. It's a bit annoying in general. And then attention heads kind of help extract this. And honestly, it is like kind of cursed. There was like, I involved in like a few subsequent papers on this. I had one Matt's paper called like Summing Up the Facts, where we thought, there'll be an attention head which based on which will kind of look at the subject and extracts like particular attributes. And what seemed to be happening is there were actually 3 different kinds of attention heads, all on the final token. Some of which looked at the subject and extracted kind of some specific things, but also just some general vibes. Some that looked at the relationship and kind of just picks up on some countries and just boosted all countries. This seems like there might be a reasonable way of doing things if you add together a vector which maps to positive logits for all countries, and one that maps to positive logits for all things related to the Colosseum. That's kind of fine. Maybe it's like not amazing, but like it should constructively interfere on Italy because that's the only thing in both. There also seems to be heads that like attends to both of them and extracts attributes from both somehow and kind of give roughly the right answer. I think there was also some other shit. And yeah. Oh yeah, there were also some MLP layers that seemed important, and I don't think we figured out what. I mostly give this as an example of how the dreams of ambitious reverse engineering held up less well than one might have hoped. Another example of follow-on is this paper called Fact Finding. Oh, really, perception thing more specific than that. That I did kind of as part of my DeepMind work, and broadly, let's see. So basically what we were trying to figure out here was kind of, is the intuitive story that you kind of get from here true? And also, can we reverse engineer what this database looks like? Like how the model stores things. Kind of, like I think superposition as a concept was like some fairly discussed at this point. We're like, surely there should be like some kind of neat mathematical structure. And we spent like 6 months there, and it was a complete clusterfuck, and we gave up. Specifically, I think we managed to understand a fair amount of what was going on. So, like, we looked at the simplified case of athletes whose names are 2 tokens, and especially ones where we think you need both tokens to figure out what's happening, like Michael Jordan. There were like these token concatenation heads that moved Michael onto the Jordan token. And then there were some MLPs, specifically a band in early layers that all seemed to do some like lookup. And then later MLPs that seemed causally relevant were actually just largely repeating this information that was already present, which you can test for with things like, can you train a linear probe to predict the sport being played on residual stream at different points? And it works okay by like layer 4, and it works pretty well up to layer 6, and it doesn't get. But like, what's actually happening in here just like didn't really go anywhere. We had some hypotheses. They seemed really messy. It was like pretty distributed across the layers. And I largely concluded that there is no reason that a database implemented in superposition needs to have a particularly nice explanation. It's a not a very complicated function. It's just mapping certain combinations of tokens to certain combinations of linear output vectors, and the MLPs want to find some way of conforming themselves to enable this mapping. But the exact details don't really need to be nice. And models clearly know many facts about many, many more entities than they have neurons. And there are also kind of mathematical constructions you can come up with how you can store way more than one fact per neuron without much error. But yeah, all right. Thus ends the tangent about factual recall. It was less nice than I hoped it might. Any questions on that tangent? Cool. All right. So, get back to here. Do people kind of get the idea of activation patching? Great. So, yeah. And this seemed like a really cool technique. And the indirect object identification paper, nope. And there it is. They kind of went beyond just looking at things like which layers matter, and were like, well, we'll look at which attention heads matter on some task. And not only that, we'll look at which pairs of attention heads communicate with each other. And because of like linear structure of the residual stream, you can make it so that one head thinks that an earlier head has changed, but everything else doesn't think that earlier head has changed. And that seemed really cool. It seemed like a really refined tool, and it seemed like they learned quite a bit about what was happening. They found this algorithm, and it later turned out that it like kind of understood the broad strokes, but they'd like missed a bunch of details and nuance. And one particularly interesting thing that kind of shifted is this kind of approach is not weight focused at all. This is using causal interventions on the activations. And crucially, it is about understanding the model in some domain. In this case, a bunch of prompts with a very specific flavor that connote a specific grammatical task. And it, yeah, I don't know. I think this is in many ways makes life much easier. because we're trying to understand what a model does on some very narrow slice of the distribution of all possible language or text. And so this just simplifies life a lot. And in particular, if some attention head is polysemantic, as a good amount of these ones are, it doesn't really matter so long as the other uses aren't featuring here specifically. But if you're dreaming of ambitious reverse engineering, this, in some ways, this seems like maybe a bit of a waste of time, where like, yeah, you can figure out what something does on some distribution, but if you don't know what it does in general, what are you doing? And I think, and I don't know, there are like a bunch of other fun things about this paper. It's a great paper. One of my favorites is, we kind of observed some weird things for the first, I think, time. Negative name mover heads, which were name mover heads were the things that found the right answer. Negative name mover heads were things that suppressed the right answer, like kind of systematically figured out the correct answer and made it go down. Anyone want to give any hypotheses for why on earth models do this? Or like what was going on? The people who don't already know the answer. Cool. All right. No guesses. So
Oh, yeah, I guess maybe there's some situations where it puts way too much weight, and then it's like with the steering vector kind of situation of like, oh, we put too much weight on this thing and that will break the model, and so I have to make sure it's not too much weight. Also, somebody had a comment with the guess.
Yeah, pretty reasonable. Let's see. Oh, sorry, my chat is not scrolls to the bottom. Yeah, with some kind of self-inflicted doubt. Yeah, there's pretty good guesses. One of, there was this delightful lab paper I supervised from Arthur Conley and Callum McDougall called Copy Suppression, where what we found was that these heads in general were annoying. People had also observed things like negative induction heads that seem to do induction and then suppress the right answer. And it turns out that the model just has a general circuit that says, am I trying to say something that occurred earlier in the context? E.g., a copy is a love, and the model kind of wants to say all's fair in love and love for some reason. I don't know. We never figured out why. Models like repeating themselves, maybe some kind of misplaced induction or copying. And then the head is like, wait, no, you're copying yourself too much. We should kill this and suppress it. And so if not that this head in any way understands the IOI task, it's responding to the heads that have figured out the IOI task and saying, you're trying to copy a thing earlier in the context. Why are you doing this? And in general, this seems like a pretty reasonable plan, but it is in practice kind of messy. Yeah, I don't know. This turned out to be a thing models do a lot. And one of the themes of this paper was like, it seemed like this head just does this all the time. Is this the only thing this head does? Have we found a monosemantic head? To which the answer is maybe. I'm not entirely sure. We tried to see how well we could approximate this head using this kind of algorithm of like, am I going to say something that occurred earlier in the context? And they got to like 77% of the impact across the distribution of like a bunch of arbitrary web text. To my knowledge, this might still be the best anyone's ever done in a language model. Kind of embarrassing in my opinion. I think people might have done better on neurons by now. I'm not aware of anyone doing better on heads. And I would consider this another nail in the coffin for the ambitious reverse engineering idea. where this was simultaneously way nicer than it had any rights to be, but also not nice enough for me to be comfortable claiming we've just like fully reverse engineered this bit of the model. Life is glorious. Yeah.
So if I understood right, what the head does is basically try to get it to not copy, because usually some other heads before end up copying that same above token. Is there a lot of examples? Like, do we have some intuition for how much of the model is trying to correct itself or is dedicated to trying to correct itself in this way versus?
Well, yeah. How much is a complicated question. One of the reasons it's complicated is like, so say this head is trying to correct itself like all of the time. These heads are trying to do name moving some of the time, and maybe they're trying to do other things some of the rest of the time. I mean, it wouldn't be too difficult to look at the direct logic attribution of, like, say, different heads or NLP layers in the model and look at which ones seem like negative on the correct answer, and where if you edit the input to that layer to remove the bits that would cause the positive logits, like you subtract the unembedding of that logit until the logit's now 0, or kind of average, or I don't know, does that make those layers or heads less likely to do this? Like, I think you could do that in like a throwaway option project, especially if you work with like a smaller, simpler model like GPT-2. More modern models have accumulated a bunch of annoying things that can make that kind of investigation harder, which is one of the many reasons fewer people do that kind of like really in-depth, let's do some maths and add things up, and like break the residual stream down into components style analysis, e.g. putting residual streams on the ends of layers, things like this. Anyway, another thing, also relevant to your question, is backup heads. Another really fucking cursed thing that I did not expect, where it turns out that if you ablate the earlier heads, even like replacing them by what happens by like replacing them with their value on a different prompt, where you say made this token Mary, so now John was grammatically correct to go here, and if you do this, then it turns out that these heads will change their behavior in response to compensate. And this is not redundancy. This is like actively self-correct. Like, this is redundancy. You have 3 heads doing the same thing, so if you delete one, the other 2 are basically doing it as well. This is more like you have a head that's either not doing the task or doing it only a tiny bit, and then you delete a head in an earlier layer, and now it starts doing it a bunch. We don't really know why this happens. It's like a pretty robust phenomena. It seems to happen all over the place, though. Like, I don't know if anyone's checked in the last 2 years whether it still happens in modern models, but I'd be a bit surprised if it didn't. Notably, this happens even in models that were not trained with techniques like dropouts. Also, we don't know whether GPT-2 Small is trained with dropout or not. It's very annoying. Even asking people at OpenAI has not been particularly fruitful. The paper implies they didn't. Their best guess is that they did. Whatever. But people have tried this on other models that don't use dropout, and it still happens. And I think that backup behavior is important for the causal interventions to understand things agenda, because it means the, well, actually, no one will tell me why the existence of backup heads is a pretty big deal. If you want to say, even if you don't care about them, you just want to identify what are the name heads.
Because if you go and you patch out certain things, it could keep working because of some backup.
Yeah, pretty much. As far as I'm aware, it's normally a dampening effect rather than bringing it to zero. Like, you'll make something, you'll be like -1 to the logic, and actually it's only -0.4 or something. So if you're really fussed about precision, you should be sad. If you just want to like heuristically figure out the important chunks of the model, this is like maybe okay. Anyway, so IOI is very popular. Couple of hundred citations. There was this whole college industry of like follow-on works doing this on different tasks. I was probably partly responsible for this, encouraging people to do it. It was also just like not that hard to play around with. And in my opinion, this became way too much of a fad, and people still really like doing it in like maths applications and stuff. And I don't think it's very interesting. I think that the like core thing that is limited about this is I think IOI actually went like unusually in depth. Most of the time people do this and they just conclude these components of the model are what matters for this task and then just stop. It's like, why do I care? I want to understand what is happening and why, not just see not just like know that these specific layers matter. And like it can be a useful tool in a broader investigation that gives you a more refined sense of what's happening. But yeah. And I think the other problem is that layers are just like a pretty coarse thing to study. And this means that e.g. if an MLP layer matters, it's pretty hard to say that much more than an MLP layer matters, I guess. So yeah, maybe going to the final thread, I think that kind of somewhat in parallel to this, people were getting pretty freaked out about what do we do about MLP layers, because we didn't really have a better plan than hope that the neurons are interpretable, or just treat it as like one big chunk. But this is clearly not a reasonable approach if you want to ambitiously reverse engineer the model. So what happened? There was the softmax linear units paper where we tried to introduce an alternative activation function that would kind of encourage the model to have monosemantic neurons. This was kind of predicated on the idea that polysemanticity was some kind of weird bug and we could probably fix it with the right thing. And this initially looked like it worked, and then after further investigation, it turned out that the model had just learned to do like superposition under the hood in more cursed ways. And this, I think the toy models of superposition paper kind of kicked off superposition being a big deal the Mech Interp community cared about. The rough, I think this is tragically a paper on toy models, clues in the name, but I think did a lot of useful work building up conceptual foundations around the ideas of superposition, specifically the idea that if you have a vector space and you want to represent things as directions, you can represent a lot more concepts as directions than you have dimensions by some kind of compression scheme. Like you shove 5 things in 2-dimensional space and you just project onto each one to see if it's present. You'll get some interference, but you can just do some error correction and get rid of it. And I think a few key insights from this paper, though it took a pretty long time before we really checked many of these things on real models, and I still don't feel like we've really checked all of them on real models, which is kind of dissatisfying. But a few insights I think are probably true. it is valuable for performance to represent more concepts than you have dimensions. You can do this by having them not be orthogonal, because, if you've got like 100-dimensional space, you can only fit 100 axes in there, but you can fit a damn sight more than 100 vectors with dot product at most 0.1 with each other, for maths reasons. And 3 Blue 1 Brown has a good video on this. That also features our fact finding. And I think that, it's even pretty inherent to performance. And this is one of the things that may be pretty pessimistic on intrinsic approaches to interpretability that try to make better architectures, at least to deal with specifically the problem of superposition and like polysemantic neurons, where it just seems pretty important for a model's performance that it represents more things than it has dimensions. And maybe if you train a much wider thing, you could get something that's like close-ish to monosemantic. But so yeah. I'll get to Jake's question in the chat momentarily. But yeah, other insights from this paper that I think are like true and useful. There are 2 kinds of superposition. The idea was kind of motivated by neurons, and the idea that you can have more concepts computed than you have neurons. But neurons, at least as we define them in Mech Interp, come after an activation function, and this means that we would kind of hope or expect that these neurons are, that they're like computing things, and it turns out they can compute more concepts than neurons. An example of this is facts, where there are just like a bunch of actually lossless compression schemes you can come up with for representing more facts than you have neurons. This, in my opinion, was first shown in one of my maths papers from Wes Gurney, who's now at Anthropic, called Finding Neurons in a Haystack. Let's see. Does this work? Yes. We have achieved set engine optimization. That just found a bunch of real examples of things like, the model has memorized that certain strings are often followed by certain other strings. Like space nan is often followed by ograms. And this is a neuron that activates on these 6 totally different substrings and boosts the kind of natural continuations. Importantly, this is like one neuron doing the same thing, and it's fine to do this because if you have a few other neurons which activate for different combinations of engrams, you can get a fair amount of insight. You can do things like say, well, if these 3 activate, then probably the like research gate engram is happening, and it can kind of ignore all of the noise that comes because each of those 3 also boosts a few other engrams because those aren't conductively interfered with. I'm conflating engrams and facts because, in my opinion, these are all just examples of memorization. Like, given a specific string, do specific thing or recall specific information. And yeah, like memorized text, engrams, facts, these are all aspects of the same fundamental thing, in my opinion. Or at least entity-based facts, where you see Michael Jordan and you recall a bunch of stuff. Yeah, so going to Jake's question in the chat about what hasn't been shown, I basically think that this is like a pretty long paper. I think it has like some interesting conceptual insights that I think are cool and worth remembering. And I think it has a bunch of other stuff that I am less excited about. And much less competent transfers. Like what do they find? Basically, I think the specific claims in this paper, I'm almost skeptical of. Like they found something about phase transitions as they vary hyperparameters in their toy model. And it goes from being, I don't even remember what. Yeah, there's like a dedicated dimension for some feature. It's in superposition. It's not there at all. The X and Y axes are some hyperparameters, and it's like these really clean, sharp transitions. Here's some funky shit. They found that if you have 3 dimensions, it can often fit 4 features as a tetrahedron. And if you have like a 20 or 50 dimensional space, sometimes it will cluster into like a bunch of different tetrahedra or antipodal pair when you've got 2 in 1 dimension. One is this axis, the other is the negation. Sometimes you have this weird shit, the everything bagel. That's right. This is the everything bagel that doesn't seem to decompose further. To my knowledge, these have not been shown to occur on real models. I basically treat this paper as a source of intuitions that I found very helpful, and then a bunch of pretty specific claims about that toy model that I think probably don't generalize. And this paper came out. It was like pretty unclear what to do about it. I think that I think you can view a lot of at least Anthropic's interpretability work as trying to rescue this initial dream of image classifying models on language models. Like, neurons, they're meaningful. Weights, they exist. You can just read them up and see the things between them. And man, it really seemed like we could get pretty damn close to reverse engineering those. And now we have language models. And in my opinion, there are just always going to be significant chunks of language models that we can't really claim to understand. My fuzzy best guess about what is happening in language models, based on just like, I don't know, being involved in a bunch of research and vibing in the field for a while, is I think that there are some properties of models that are kind of salient and important, and these are often pretty easy to pick up on via a bunch of methods, like sparse autoencoders, often like probes or steering vectors, or even just like literally talking to the model. And then there's a separate cluster of stuff that's more like what I think of as like a really long tail of bullshit heuristics, where like maybe the model has some like really nice coherent algorithms, like the IOI thing or addition circuitry and things like this. Things that's like pretty coherent to solve tasks. And there, you have my t-shirt of the days of the week, represented as beautiful points on a circle. You can buy your own at Interp shop. And not joking, it's surprisingly easy to make your own merch store. And yeah, there's like some really nice things that seem really important, and we can understand them, and this is like actually pretty damn useful if you want to do something like model biology, or like apply this to useful tasks, or understand the broad strokes of what's happening in models. But there is just a lot of bullshit, like the error term in sparse autoencoders and the backup stuff and weird second order components like copy suppression and stuff we haven't even got to in this, like kind of heuristics that are like slightly useful and thus why here, because if you got weights, why not use them? And I just don't feel like the quest to understand as much of that as possible has gone particularly well. But given that I have been going for coming on 2 hours, I'll probably wrap up there and continue probably I'll probably spend some time tomorrow, and just move whatever other event I have tomorrow to talk about kind of the dictionary learning saga, and then what I think are the most exciting directions now, and like what's been happening recently, and what I'm actually optimistic about, and kind of what I see as the current burgeoning directions in the field. But yeah, I know. Happy to take any questions if people have them before wrapping up. Gerson, if I'm pronouncing that right.
Yeah, I usually say person, but with the G, so Gerson. Yeah, I was curious what your thoughts are. I guess like there's still this circuit thread is still pretty active, and I think there's a lot of the recent work has been focused. I guess
I will discuss dictionary learning tomorrow.
Okay, I guess my general question was like, what are your thoughts on the general direction of this thread, and like the work they're focusing on? But maybe that's for
It's dictionary learning.
Okay. Yeah.
Come to the thing to work.
Okay.
But I probably should not try to give an answer that will just turn into me giving tomorrow's thing. But it's an excellent question. But I basically model Anthropic as being almost all in on dictionary learning, at least kind of Chris Oler's interpretability team, with some other parts like Jack Lindsay, who invented a bunch of stuff like cross-layer transcoders and crosscoders, now has a AI psychiatry team that's doing stuff that I consider much more within the domain of like pragmatic interpretability. And they did a bunch of like really cool shit in the Claude Sonnet 4.5 model card that came out yesterday, kind of investigating it for eval awareness. Yeah, I think the question of what do I think of their agenda, basically what do I think of dictionary? There are other things like Lee Sharkey at Goodfire doing his like stochastic parameter decomposition. That's like another flavor that I don't know, I kind of have in my category of, well, maybe it'll work. There are a lot of things in the maybe it'll work category. It's good if people who have conviction about some direction go work on this, but I'm pretty happy to leave it to Lee until he has epic results that will convince me to drop everything and pivot. Like I did for like a year based on SAEs before deciding that was probably a bad idea and I should do something else. Any other questions? Alex?
What do you think about the early universality claims? And I guess how come they haven't been followed up as much? I feel like I haven't seen them much in the newer literature.
Yeah. My take is basically universality seems like somewhat but not fully true. I don't massively feel like it's that decision relevant for how I would approach understanding models because of the not fully true part. I think people often just kind of take it as a given, I'd say, or like it's often kind of assumed that studying some phenomena in this model is interesting because probably generalizes. I think nowadays people often study multiple models. I like to hope that transformer lens making that really easy helped make this a norm in the field, which I think has been like very good for epistemics and like research culture in the field. But like so one answer to this is just actually most papers are also universality papers because they just check their findings on a few models. But it's more like high level universality rather than like super in the weeds. There have been some works on this. Ones I'll highlight. There was this fun paper called like Rosetta neurons that kind of tried to look at neurons in different image classifying models that were very correlated and said, these are probably interpretable because they're representing a concept that's shared between them. So probably it's legit. And did some interpretability of these. And this is a cool paper. Yeah, like I think this is a bunch of neurons that all seem like pretty similar and correlated. I don't know exactly what these show, but I'm sure it's halfway rigorous. And there was a fun paper from Wes, one of my alums, on universal neurons in language models, kind of doing the same thing on this family of like 5 GPT-2 small and medium models trained with different random seeds, finding, just like a bunch of interesting stuff, like neurons that really liked letters, or possibly words that began with letters, I can't remember. Or, something about, does the previous token have a comma? And I think these would both be just like across a bunch of web data. So this is like pretty monosemantic in my opinion. This one, is a year, where I guess it lights up if it's not a year. This isn't activations. This is the direct logit attribution of the neuron. So like you look at all of the tokens, it impacts on logits, and years are negative, non-years are not. So this is a don't see a year neuron, which is important in GPT-2 because the way tokenizers worked, at least back then, is it was purely based on which substrings were frequent. Can anyone see why this might make you want to suppress years? If you have no special handling for numbers, but you're just like, which strings are common? Anyone? No? All right. So basically, what goes wrong is that the string, say 2001, is way more common than an arbitrary 4-digit number. So that is a token. Most 4-digit numbers are not. And but it's also a number, and thus the model will have kind of it will need to be really careful about what kind of number it is currently talking about. Where, e.g., it kind of just needs a bunch of like spectral handling for like what kind of number it should be tokenizing right now. And sometimes you get unlucky and you have a normal number that just happens to have a year in it. And sometimes trying to like write data by hand can fall into problems like this. Could you type like 123 or 1, 2, 3, 4, 5, 6, and like that's probably a token. And so that's very different from how the model would deal with an arbitrary 6-digit number. And so why exactly it would want to suppress years is like not nearly obvious to me. I could see why it would want to suppress non-years if it's like, this is definitely a year. And plausibly it wants to sometimes correct for that kind of machinery, or sometimes maybe it's saying a date and it could either say a year or it could say a month, and there it wants to like not say a year. Though that one isn't really about number tokenization. That's just like a reasonable thing to do. Anyway, nowadays, many models either just have each digit be its own token, or have, say, every number between 0 and 999 be a token, and every other number not be a token, and needs to be broken down. I think I can't remember which models do which. This is an extremely important thing to check if you are ever doing research like this with numbers. Generally, a thing you should just very frequently be doing if doing any research that is remotely kind of hands-on with the model is display things with like boxes around each token or some other indication of like how it's tokenized, like using the transformer lens, like to stir tokens or something. But yeah. All right. So going back to universality, basically, I think I want to say it is a thing. You know, like a thing reviewers will typically complain about. It's like, why did you only look at one model? That's dumb. And I think this is a reasonable thing for reviewers to complain about. And this also applies to your sprints. If you can show me the or like the more surprising the thing is, the more I care about seeing it on multiple models, I think. Yeah, I know, like one fun example would be the like refusal is mediated by a single direction paper, while I'm just doing a core of my maths papers as of a year plus ago. Where our like figure one was just, we look at a bunch of models and refusal sure seems to be represented by a single direction, guys. And I think this was pretty important for making the case that, yes, this is just a thing about models that is pretty general. Maybe it doesn't apply to every model, like proprietary frontier lab models probably use interestingly different fine tuning than like open source ones, but like, yeah. Anyway, in universality seems mostly but not entirely true. Occasionally papers look into it a bit. Many papers like casually investigate it. And papers that don't often get criticized as being less rigorous, but it's not seen as like a major basic science research direction that would be like super important. I don't know how satisfying an answer that is.
Good.
Yeah. So this is basically why I'm not particularly excited for sprint projects on this. I just don't expect to learn that much. Alan?
Well, I guess one follow-up question about universality, and I remember that like there had been these like universal adversarial examples, image models, and I guess that's kind of a different thing from here of like this like meta universality about like some concept. But I guess I'm curious whether that appears like universal jailbreaks or stuff like this in LLM context.
Yeah. So that is a complicated question. So I think, okay, so first off, I think we should distinguish between interpretable adversarial examples and gibberish adversarial examples. Why I would consider the shark baseball one to be an interpretable one. Let's see. Another one of my favorite examples is the multimodal neurons paper, where actually, let's go to Google it. This is such a badly SEO'd paper. And yeah, so this is a adversarial example for a multimodal model that's basically trained to take images and text and say, is this an appropriate caption? The latest Apple iPod, clearly. And I mean, this iPod is like non-trivial already. But this is a model called Clip, which was it was like one of the key things used to make DALL-E, which was one of the first like big deal image generation models. Sorry for everyone who just knows this history and I'm just patronizing you, but completely interesting context for people less steeped in the weeds. But anyway, so there's some churchful ones, and then there's the like probably if I just Google adversarial examples, you'll see the airliner pig. The interesting so there was this delightful paper called like adversarial examples are features, not bugs. Not bugs, they're features, which has inspired many copycat titles. And one way to think about the findings of this paper is basically saying, we think there are real interpretable concepts that are common to these images that adversarial examples use, that models use, that humans can't perceive. And I admittedly ignored this paper in detail. That could be an incorrect summary of exactly what it says, but it was kind of like postulating the bold hypothesis that like all adversarial examples are actually reasonable interpretable things. And I think Yeah, another fun thing Distill did is they had a kind of thread of different researchers responding and doing follow-up work on this. But so adversarial examples of language models. One of the first papers that I saw go properly viral on this was the like GCG paper, which yeah. No, yeah, that's not a year, it's just the citation count. 2018. And yeah, they had the like particularly spicy claim that not only could they do so they kind of produced these garbage suffixes. For example, that just kind of look like nonsense. Maybe this is that kind of thing. So, it's not quite what I call an interpretable adversarial example. But it, in fact, generates a plan to destroy humanity, though not necessarily a good one. But this was before you could just, in fact, tell the model to help you make a bioweapon, and it would give you useful answers. As is apparently the world we currently live in. But yeah. And so this paper existed, it made a splash. I still don't really understand to what degree this paper was legit or not. I gather a fair amount of people could replicate it on like a single model, but couldn't really replicate the universal thing. But also it's like a really fiddly thing. And also, at least on like single models, many of the seemingly fancy things done in this paper don't really seem that important. Like GCD stands for like greedy coordinate gradient descent or something. And the idea is like, you're using gradients to estimate which tokens are more important, are like better at being a like weird cursed suffix for fucking with the model. And it turns out, actually, exercise for the audience. Suppose you have you're reviewing a paper that's come up with this, and you're like, I think this method is way more complicated than it needs to be. What is a simplification you could suggest they do that plausibly would also work? Where, to recap, the method is essentially you use gradients to estimate which token. You start with like a randomly generated suffix, and then you use gradients to estimate which token, if it replaced the current token in some position, over all positions would be like most important, and then like swap that in, and then keep doing this.
They just do like MCMC, for instance, or some like, like have some target function for your acceptance of changing a token to another one.
So sorry, so what exactly would your method be here?
Oh, it would be like pick a token at random, pick a position at random, pick a token at random, substitute it, and like keep it if this, according to some probability, activated by like Metropolis Hastings or something. Maybe not even just do a random walk, but like you could steer the random walk by using like, Metropolis Hastings or something.
Pretty much. Basically, I at least believe there was some private follow-up work. I can't remember if anyone did this like properly publicly, where you just replace it with like, well, let's just like randomly mess with tokens and see which ones work better. Do this like 100 times from your starting prompt, and then keep the one that's best, and then just keep doing this. And this is pretty competitive because I don't know, gradients just aren't very good for tokens. Token space just doesn't seem particularly linear. It's weird and cursed and discrete. And yeah, I don't think you necessarily need things like Markov chain Monte Carlo or Propolis Hastings or whatever, you can just literally try 100 random steps, keep the best one, repeat. Yeah, this is a useful lesson in if you think you have like a really complicated fancy method, maybe it is a lot more complicated than it needs to be. I don't know. Yeah, some other fun examples of this. There was an unlearning paper that claimed that it was finding the like bioterrorism novice versus bioterrorism expert steering vector and like subtracting that, and that's why it works. Can anyone see the natural relation on this one?
So it worked to do what?
They wanted to make the model bad at like helping with bioweapons. So they found a vector that was supposed to represent like kind of knowledge of bioweapons, and then they like subtracted it with a big coefficient, and then the like score on the bioweapons benchmark went down much.
But I guess they made the model stupid in the way that you do by adding a large steering vector. Or it's a possibility.
So that's one hypothesis. Yeah, okay, maybe everyone just take like 30 seconds to think on their own about how exactly you might test the hypothesis that that's what they're doing. Or like, what simplifications could you make to this?
Maybe
I want people to get a chance to just think on their own for a bit. All right. Anyone bonus points that you haven't spoken before want to give a guess? All right, people who have spoken.
Yep. So instead of steering, maybe I would just fine tune it.
Yeah. Well, so that's more like a baseline. I'm trying to ask, how would you tell if your method was more complicated than it needed to be? Or like it, and you could just fine tune instead is an answer to this, but it's more like you didn't need to bother doing the complicated.
I think I know the answer. Just like I'm hitting a cache that's saying you add a random vector.
Yeah, pretty much. You replace the vector you believe has meaning with a random vector. Performance is unchanged. Therefore, you were just making the model dumb. Replace the vector you think matters with a random vector is a extremely good baseline that you should basically just do if you ever think you have an interesting vector that's giving you interesting results. It's also just really easy because you can just take whatever their other line of code is and put torch.randn like around it or something. Maybe like scale it to be the same norm, because norm can matter quite a bit. But yeah, random baselines, highly underrated research technique, would recommend. They're also really easy. Ditto things like, well, what if we just like randomly selected a chat prompt to give to the model rather than our like careful handpicked one? Or what if rather than looking at the model on this biology data, we looked at it on random chat data? Would our bioweapon detector also light up there? That kind of thing. All right, so I think I have somewhat gone off the rails. I was answering a question about adversarial examples. Obviously, there are many interpretable adversarial examples. Like, typically when people say jailbreak, they mean interpretable. Or at least you can kind of reason about why it works. I'm not aware of the good interpretability work on these kinds of suffixes. We looked at it a bit in the refusal paper, but didn't really make that much headway. Like, there were some components that seemed important, but kind of run into the classic problem of, well, you found the components that matter, but what now? And yeah. All right. So yeah, I don't know if I have anything more to say here. I don't know how satisfying an answer that was.
You mean like you found the directions and then what now? What do you mean? Like, where would you want it to go?
Yeah. Oh, no, sorry. You asked a question ages ago about adversarial examples, and I'm asking, does it feel like that question's been answered, or is there like more I could?
Well, I guess, I was curious about your last comment of like, what do you mean, what now? Like, where would you want it to go if you found the examples? Like, you'd want like an interpretable way to stop them, or way to understand like what they're doing in the model, or
Yeah. So the thing, I guess the main thing okay, so like, there's the thing that with my ambitious reverse engineering hat on, I'd want to do. It'd be like, why? Why is it the case that this string gets the model to do this? Why is it universal? And you might try things like kind of doing ablations on the string and figure out the simplest form. And you might think that you can like run an SAE on it. I don't actually know if anyone has tried literally that. Probably someone has. It would be an interesting thing for someone to play around with. Probably just like a throwaway afternoon project. I recommend not trying to replicate GCG because it's a pain in the ass. But you can probably replicate the like random search version pretty easily. Or just find some examples online, or just literally try giving this to a model and see what happens. And just pick one of the models we have SEs for. Though also you should probably get a model to do a lit review for someone done this. But yeah, I think one answer you might aim for is how is the model disrupted? Either there are attention heads that don't do the right thing anymore or whatever. Another thing you might do is like, oh, well, what are the tokens where the crucial thing happens? As I do patching, how does that matter? Which we did here. And another would be, what do I say? I think that you might want to take and you can like see if there's some representations that become interpretable. One thing you might want to do is try replacing it with the SAE reconstruction. And if that works, then that's some evidence that it's interpretable. If it doesn't, that's some evidence that it's going via some like weird ass mechanism. One hypothesis put forward has been that adversarial examples sometimes come from superposition gone wrong. Like you have that like sometimes there'll be some features that kind of using similar directions because they don't tend to occur at the same time. And maybe an adversarial example has learned that by making one of those light up, you can make the other one light up. And that's enough to break the model. It's an open question how much the structure of superposition is universal between models. Like how much you'd expect this kind of overlap to make sense. So you could probably try answering it by, I'm sure someone put out a set of SAEs with similar random seeds, or like with different random seeds, but everything else the same that you could study for this or something. And, no, what you'd want is two models with SAEs. Probably what you'd actually want is like a crosscoder between two different models. And then the crosscoder should have a direction in both models for each concept. And then you can look at the like cosine sim between those directions for different models and see whether that's consistent-ish or not. Yeah, I think that might get you probably tell you something. But it's like less obvious that those kinds of adversarial examples, if they even exist, should work. They should be universal. And overall, I am pretty pessimistic on there being like a really nice explanation down to the kind of token level of why this stuff works. I think it's plausible that there's more of like a model biology explanation of like, well, at layer 10, the SAE latent for this is great, guys, has lit up a bunch. And if you get rid of everything other than that, that's sufficient for the jailbreak. Therefore, this is the important thing. We have no idea how that thing is activated. Shrug. But yeah. The reason I'm not super excited about sprint projects on this is I just don't think adversarial examples are like that important. Like, I don't really know what it would change for like me or people trying to make safer models to have a better understanding of where they come from. I think the jailbreaks are, well, first of all, I'm just very pessimistic about the ability to fix adversarial examples because thus claim the adversarial robustness researchers that they have tried doing this for like a decade and failed. And I think that generally just like being robust to adversaries is really hard, even if you can make their lives harder. I think that there are things that are more like probe for how someone got the model to do a bad thing, no matter what the means were. And like, I think that's just legitimately useful. And like a perfectly valid direction of applied interpretability. But I feel like those kinds of defenses are better off being agnostic to the form of the attack, especially as it's harder to do this kind of attack on like frontier models because they tend to be closed source and adversaries won't have access. So maybe you can do this by just hitting the API a lot. I don't really know. All right, how satisfying was that answer?
I definitely have more questions, but I also like don't want to keep taking up time.
All right. Anyone else? I think someone had their hand up. All right, I'll take one final question, and if no one else has one, it can be from Mel. Seems like no one else has one.
I guess just on the last thing, I mean, I guess you can imagine like attacking probes, right? With like adversarial examples. So like if you had like techniques for detecting whether a user is doing something bad, those could be adversarially attacked, and like that would, I don't know, break that defense.
Yeah, so I think that to me, the interesting question is it's not can you break probes, but it's what affordances do you need to break probes? I think if you give me a full white box access, yeah, I know. We basically know that you can optimize inputs to make numbers go in arbitrary directions. People have shown this. I was not very surprised. There are, some methods that have like somewhat more aggressive version or like more universal versions of this, but they still depend on like having this kind of privileged access. The thing that I'm really interested in is with like an API or just clumsy access, the kinds of things people would have on, say, Claude if it is deployed with probes, which I think it probably is. And yeah, if people then were trying to like break into that, even with like arbitrary amounts of prompts, like maybe you do an evolutionary algorithm and then we try to figure out how hard it is to break that, I'd be interested in that question. It's plausibly harder to do this on APIs because you either get rate limited or they tell you, or they notice when you do jailbreak it and they're like, fuck you, we're going to revoke your API key. I'm not entirely sure. I'm sure someone's tried a kind of black box random attack on APIs. And I'd be kind of curious if it works or not. But yeah. Yep, as a question I'm interested in. I generally think that regardless of whether anyone is currently using probes, it does not seem like people have been using probes in production for long. And I think that over time you would, like if you introduce a new defense, it's going to look really good because people have spent ages breaking the old defense at safety training. And so this is a problem, and I'm pretty curious whether over time we're going to figure out new classes of jailbreaks that suddenly started working on models at some point. That presumably corresponds to when that model started using new defenses like probes. I don't know. Yeah, I do think this is a weak spot in a lot of research into things like monitoring and defenses. Like, you need to check whether your thing is robust to realistic adversaries. Otherwise, you're going to get a significantly inflated view of how good your thing is. And maybe that's okay if you're not going to be up against adversaries, or you will just do incident response and you think you have good incident response, and if this is an issue, you can deal with it, or just like switch back to an older, more expensive kind of defense that's hard to break. But I don't know. Papers often don't check this kind of thing, especially academic papers. A lot of readable to check. And people often also don't check things like what's the false positive rate on random user traffic, because you really don't want your bioweapons detector going off on 5% of users. Or yeah, like kind of what's the runtime cost, or what are the side effects on the model if it's kind of more of like a change to the model, and bunch of questions. All right, I'll wrap up there. Thanks all for coming. And yeah, I'll put something in the calendar for tomorrow.